This set of notes is about Faraday's law. Set of notes has been provided for you in Schoology. You can use those or you take your own. You know the drill. All right, so Faraday's law, as you hopefully figured out from the POGO, is simply redox stoichiometry. So using stoichiometry, we can determine the number of moles or mass of a chemical used or produced in an electrochemical cell over time. Okay, so some important terms and definitions that are going to be important to us in using Faraday's law. One is the current. Okay, the current is the electric charge transferred per time. So in other words, how much electricity is transferring through a wire or through a solution in an amount of time. The unit that we use for that is the ampere, which is equal to 1 coulomb of charge per second. Second term that we need to know is voltage. Okay, this is the energy transferred per unit of electric charge. So this is a measurement of how much energy do we get per coulomb. And we may use the volt to measure that, and the volt is a joule of energy per coulomb. And the last is the Faraday. Okay, the Faraday is simply the electric charge of a mole of electrons, and that's where we get Faraday's constant from. So Faraday's constant is that we have 96,485 coulombs per mole of electrons. Right. Also important to note, the unit on this, if we do some rearranging with what we have up there on the top, we can actually see that a coulomb or a Faraday's constant can also have the units of joules per mole volts. Okay, so that helps us out in some situations, but not others. All right, so using stoichiometry, we can determine the number of moles or mass of a chemical used or produced in an electrical chemical cell over time. For example, the other day when we talked about electrolytic cells, we talked about this one where you can actually get copper plating on the cathode over here through electrolysis. So the question that we might ask is, if the cell on the right were to run with a current of 10 amps for 30 minutes, what mass of copper would be deposited on the cathode? Okay, so the first thing we recognize here is they've given us a current, amps, which is an amount of charge per second, and they've given us a time. Okay, so from that information, we can figure out how much charge or how many coulombs of electricity, how much charge we put into the electroplating. Okay, well, what carries the charge in our reaction equation? Well, it's the electrons. So since this is a redox reaction, we know that electrons get transferred by adding the charge to them. So we can go ahead and let's take a look at our equation here and figure out what's going on in the redox reaction. All right, so the first thing I'm going to do here is I'm going to figure out what are my two reactions going on. And that depends upon us knowing that this copper in aqueous solution is going to become copper plus 2 and 2 chlorine minus ions. All right, and so we can go from there. So writing my equations, so obviously we're going from plus to neutral there, from negative to neutral there. So here we are going to lose electrons, and here we are going to gain electrons. So this is our reduction, and this is our oxidation. All right, so if I rewrite that, given that information, here become my two half reactions. Copper plus 2 electrons goes to copper solid, and 2 chlorine ions goes to chlorine gas plus 2 electrons. So in this first equation, you can see that we are gaining electrons, so this is our reduction. Bottom one, we are losing electrons, so that's our oxidation. It doesn't really matter which is which, but what we've effectively done now is we've created mole ratios between our number of electrons and each of our substances. So if we can figure out how many moles of electrons were transferred, we can go ahead and figure out how much copper is being deposited or how much chlorine is being produced. All right, so how do I do that? Well, I look at what they gave us up here, and I know that they've started with 30 minutes. We know that 10 amps, by definition, is 10 joules per second. So I'm going to write that as a conversion. 10 joules equals 1 second. All right, and we'll start with that to begin with. Okay, so I'm going to go ahead and I'm going to start with my 30 minutes. and I'm going to put that over 1, and then I'm going to use this over here. Well, I got to get rid of minutes first, so I'm going to go with 1 minute equals 60 seconds because I'm trying to get to something that has seconds in it. And then I'm going to go 1 second equals 10 joules, okay? And sorry, not joules per second, that should be coulombs per second. Should be 10 coulombs per second. Okay, so minutes cancel, seconds cancel. I'm left with coulombs of charge. Well, do we know anything else about coulombs of charge? Well, yes. We know that 96,485 coulombs equals 1 mole of electrons. Okay, so I'm going to go 96,485 coulombs per 1 mole of electrons. Okay, well, now I've gotten myself to moles of electrons. So now I can just use a mole ratio to get me from there to copper. And so from our balanced equation up here, we know that 2 moles of electrons equals 1 mole of solid copper. And last thing we would need then would be our molar mass. 1 mole of copper equals 63.55 grams. Okay, moles of electrons cancel. I'm left with moles of copper cancel. I'm left with moles or grams of copper. So now I just have to do my calculation. And that gives me a final answer of 5.927, et cetera, grams. I get 3 sig figs here, so this becomes 5.93 grams of copper. All right? So big thing for us to understand here is, again, that the amperage can give us the coulombs per second. Faraday's gives us the coulombs per mole of electrons, and we can then use that to figure out some stoichiometric ratios. Okay. We can also do this process in reverse to figure out amps from grams produced. So likewise, if they told us that we had 5.93 grams of copper, we could then go 63.55 grams of copper to 1 mole of copper. Then use our balanced equation. So 1 mole of copper is 2 moles of electrons. Then use Faraday's constant. 1 mole of electrons is 96,485 coulombs of charge. Okay, and then from there we would need to go and divide our coulombs by time. Well, from our previous problem, we know that the time that happened was 30 minutes. Okay, and so we could divide this by 30 minutes, and then we know that amps is in coulombs per second, so we would go 1 minute equals 60 seconds. Okay, that's then going to leave us with a unit of coulombs per second, and if we reverse this entire thing, we should end up coming up with an amperage of 10 amps if we do the calculation. So that's what Faraday's laws are and how we use Faraday's laws in stoichiometry to determine how much of a chemical is involved in an electric redox reaction.